Swayam Prabha. Digital India. Educated India.
We will continue our discussion of this Taylor dispersion problem that we were discussing, and we will look at things more quantitatively. Yesterday I was just giving you the broad idea of what are the physical processes that we need to include in our analysis. Now we will do with some equations. Okay. So, clearly the equation that we have to solve is the energy balance equation, because we are looking at how the temperature in the slug is going to change with position and time. Okay. So, the energy balance equation is the Taylor dispersion and equation is basically dt by dt plus we are talking about a fully developed velocity field Hagen-Poiseuille. Okay. So, only the Vz component is there, and that is going to be given by 2 times u times 1 minus r squared by a squared times dt by dz equals alpha times 1 by r dr plus d square t by dz square. So, what are the assumptions we have made? One is I am not considering any theta variations. So, there is theta symmetry in the system. Okay. So, basically look for theta symmetric behavior. What do I mean by theta symmetric behavior? There is no change with respect to theta for velocity and temperature. So, if I look at the cross section, if I go in the theta direction at this theta and at some other theta, the velocity will be the same. Okay, the temperature will be the same. So, that is the reason there is no theta dependent term here, otherwise there will be 1 by r squared d squared t by d theta squared. This is coming because of fully developed profile. So, if it is fully developed profile, only the Vz component is there, and long back we derived there will be no radial component of velocity, there is no theta component of velocity. So, all the other gradient terms do not show up, okay, and there is no reaction, no heat generation. This is my energy balance equation. What I want to do is I want to make it dimensionless, okay, because the whole idea is I want to find out what are the terms, what are the effects which are dominant, okay, and one way to do it is to make it dimensionless. So, the characteristic length scale RCH is A, because that is the radius of the tube. This is the tube radius, and ZCH also I am assuming it to be A, okay, right now. What else do I have? Temperature, I am going to define theta as T minus T1 divided by T0 minus T1. This is T1 is outside and this is in the slug. Okay. T0 is at high temperature inside the slug, T1 is the temperature outside. Do I need to make anything else? Length scale is done, temperature is done. I am left with one more thing. What is that? The time. Time also has to be made dimensionless. For that, I am going to choose TCH. as, because the convection involved, I am going to define my time scale as A divided by U. Okay. I mean, you could also do A squared divided by kinematic viscosity, for example, or A squared divided by alpha, but right now I am just doing this. Okay. So, we want to substitute this here and convert this. So, because this equation is linear in temperature, okay, to the power 1, derivative to the power 1, all these are to the power 1. When I substitute for t in terms of theta, what will I get? I will get T naught minus T1 multiplying every term. Okay. This will become T naught minus T1 d theta. So, basically I am saying T naught minus T1 is going to be there in every term. I will do it once, but next time I am not going to write it. Okay. So, T naught minus T1 times d theta, and dt will be, T characteristic will come out from the denominator. So, I am going to get U by A, okay, plus, and remember this is the average velocity, this is not the max velocity. Max velocity is 2 times the average, that is what I have written. Okay. This is average velocity and 2u is the max velocity for a parabolic profile in a circle. So, I have plus 2u times, again theta will give me T naught minus T1 divided by A times 1 minus r star squared times d theta by d z star, and I should put T star here. T star is dimensionless. Okay. So, what is T star? T divided by TCH. Yeah. Okay. Now, this equals what? This equals alpha times, since I have second order in the radius, I will get A square here, and this temperature will give me T naught minus T1. So, I am going to take out T naught minus T1 by A squared times 1 by r star d by d r star of r star d theta by d r star plus d square theta by d z star squared. Okay. What have I done? Just made it dimensionless. So, like I said, I am just going to do this once, although the T naught minus T1 here. And there is an A squared here. Okay. So, T naught minus T1 cancels everywhere, and what I am left with, I am going to take A square common from both sides, from both these terms, and multiply this by A squared alpha. So, I have U A squared by alpha times A so this U by A is common. Okay. I can take U by A common outside, I get d theta by dt star plus 2 times 1 minus r star squared d theta by dz star equals the conductivity term, which is 1 by r star d by d r star of r star d theta by d r star So, I have just multiplied, I have taken the alpha by A squared to the other side. So, multiplying throughout by A squared by alpha, okay, and U by A is common. This is what I get. This, remember, is nothing but UA divided by alpha is my Peclet number. for heat. So, this is Peclet number multiplied by d theta by d t star plus 2 times 1 minus r star squared d theta by d z star equals del star squared theta. Okay, del star means everything is in terms of dimensionless. So, when supposing these characteristics variables that I have chosen are indeed correct, then what does it mean? It means that each of these terms, this d theta by dt, this term, this convective term here, the second derivative conduction term, all are of the same order of magnitude. Okay. So, the only parameter which is going to decide which is significant is the Peclet number. So, if Peclet number is high, what does it mean? This convective term, the left hand side dominates, I can neglect conduction. Okay. So, for high Peclet number, for Peclet number much greater than 1, conduction can be neglected. Okay. What is Peclet number? UA by alpha. So, alpha is quite small, okay, and even for moderate velocities, low velocities, Peclet number will be high. So, Peclet number greater than 1 is not very strong, severe assumption, it is usually valid. Okay. The only thing is, so if this is the case, then here under these conditions, I will say d theta by dt plus 2 times 1 minus r star squared d theta by dz equals 0. That is, I am dividing by Peclet number is large, so this will go off. So, what this means is your conduction terms can be neglected and you only have the unsteady state term and you have the convection term. Okay. So, here convection dominates. Now, all of this is valid as long as this assumption that this choice I had for z characteristic being equal to A is correct. Now, z characteristic will be equal to A only for the initial portion, because when the liquid is just entered or the slug is just moving, the distance over which the liquid has moved, the slug has moved is A. Supposing, and therefore, only for short times, the assumption of z characteristic being equal to A is going to be valid. So, my point I am trying to make here is convection is going to dominate for short times. Okay. What is the meaning of short times? The time is going to be given by A divided by U, because my z characteristic was A, my mean velocity is U. So, this is true when z characteristic is A. Okay. That is, the slug has moved a distance axially of A, and what is the time? This is for t is going to be A divided by U. So, only for this initial time when t is less than A by U, A is the horizontal distance moved, U is the horizontal velocity. So, only for t less than A by U or t star, which is t divided by t characteristic less than 1, we have this situation. Okay. So, this business of convection dominating, where I can neglect conduction, is only for the initial part, low type. What do I mean by initial part? This T star is less than 1, T is less than A by U. Okay. So, that is the initial portion. Why? Because only here is my choice of Z equal characteristic being equal to A valid. Okay. Now, what we saw also is that far downstream, I mean if you wait for a sufficiently long time, the slug has moved. Okay. For large T means a long time. In this case, the slug has also moved sufficiently far. Okay. So, that is T much greater than A by U and Z much greater than A. Okay. The slug deforms to a large extent at r equal to 0, because velocity is maximum there. You saw that yesterday, right? Because this parabolic profile, high velocity, that these high temperature will have. So, if the distance in the axial direction is large, then what happens is, in the axial direction the conduction will be slow. For example, if you have some temperature here, this distance is large, the conductive flux is going to be very low. The resistance is high because the length is high, whereas in this distance is very small. Okay. So, it will flow faster. So, my point is, when you have this kind of a situation, because the slug has moved, okay, in the center, the Z characteristic becomes much higher than A. So, the conductive resistance in the axial direction is high, conductive resistance is high. So, heat transfer by conduction in the axial direction is going to be very low, but in the radial direction the distance is small. So, heat transfer by conduction will dominate. Okay. So, here axial resistance to axial conduction is high. Okay. But and resistance to radial conduction is low. So, basically here the distance it has moved axially is large. Okay. And therefore, basically what I am saying is, radial conduction dominates and radial conduction dominates and axial conduction is low. Okay. So, that is the situation. So, I think the point I am trying to make here is, there are many problems where the physics of the problem changes. For a particular problem, different effects become important in different domains. Okay. So, this is something which you have to understand. So, for low Z, convection dominates, we neglect conduction. For high Z, radial conduction dominates. Okay. So, basically the physics changes depending upon your position. Okay. So, the important physics changes. Okay. And we saw this problem when we were doing the grids problem also. Okay. So, now the question is, you have seen a similar situation earlier when you are looking at boundary layer flows. The boundary layer flows when you have a flat plate and a far upstream velocity moving. Okay. Very close to the wall, very close to this plate, you will have the viscous effects dominating. So, you consider a thin layer, the boundary layer, and then you solve for the Navier-Stokes equations including the viscous effects. But far away from the wall, far away from the plate, you will say the flow is inviscid. Okay. So, and then you assume that the far upstream velocity u infinity is prevailing everywhere, you neglect viscous effects. Okay. So, this, what I am saying is there are many problems like this. This is similar to boundary layer flows. Near the wall, viscous effects are important, far away flow can be assumed inviscid. Okay. So, just like you are neglecting conduction kind of thing, momentum transfer by conduction far away, okay, only convection, but here there is also conduction, viscosity is like conduction, mu d square u, second derivative, okay, momentum diffusivity, conduction is thermal diffusivity. So, that is the kind of thing. So, the point I am trying to make here is there are many problems where you will have to solve for the sake of getting a better understanding. If you have good physical insight, you will solve a different set of equations in different regions. Okay. And then what you do is you want to get a complete picture, you solve in this region, you solve in that region, and you try to match. Okay. So, there is this technique called matched asymptotic expansions, which people use mathematically to solve. So, you can do this matching and you can get the complete picture. Of course, you do not want to do all of this. You say I have a beautiful computer, high performance computer, I will put my numerical code and try to solve, you can, but if you want to capture the resolution, you may have to go for finer and finer grids. So, you know, it is like you want to go very near the boundary layer, you may need to take very fine grids, computational costs go up. So, there is a trade off. Okay. So, rather than do blind computations to get the picture, you can do this, do a solution of one set of equations in one domain, another set of equations in another domain, and then try to do a matching. Okay. And we do that in boundary layer theory. But what we are going to do is we are not going to do any of this. So, you can be relaxed. We are going to look at this end and we are going to look at that end, that is all, no matching. Okay. So, let me see, what did I have? D theta by dt plus u star dot del theta star, okay. And what did I have here? U by A, is that right? No, I am going to write that side also, then Peckley will come. So, okay, let me write Peckley. Yeah, let me just jump directly to what I have. Peckley number into this, right? Times del star squared theta star. So, this term, remember, the way you have to think about it is, this term represents the convective term, okay. So, convective term is the left hand side, conductive term is the right hand side. So, convection by conduction divided by conduction is this divided by this. Okay. And what we are saying is, this is of order 1, this if I have done the scaling properly, this will be of order 1, this will be of order 1. So, they are of the same order of magnitude. So, basically they are not going to be of different orders, this is what we are assuming if you have done the scaling properly. So, these two will basically cancel off, and this is Peclet number. So, rather than do not look at Peclet, his question was, look, Peclet number is this divided by conduction, looks like conduction divided by convection. No, this whole thing is convection, this whole thing is conduction. So, you divide that by that. See, when you did Reynolds number, we got Reynolds number as du by dt plus u dot del u equals del squared u in dimensionless form. Okay. Again, this whole thing is my inertial term, the left hand side is my inertial term, the right hand side is my viscous term. So, you say Reynolds number is the ratio of inertial to viscous. Okay. So, basically inertial force, so inertial to viscous is Reynolds number multiplied by du by dt u dot del u divided by del square u, and that is basically order 1 both, okay, and I get that. So, that is the way to look at it, okay. Good. So, now what do I do? I am going to take my energy balance equation and rescale it. I am going to keep everything same, only thing is the Z characteristic is not going to be A anymore, because Z characteristic, I know it is going to be much larger than A, okay. So, since I do not know what it is, I will just choose it as L, okay. So, we rescale the energy equation choosing Z characteristic as L, which I do not know yet. I have to decide what it is, okay. But I know this is going to be much greater than A. So, let us go back, dt by dt plus 2u times 1 minus r squared by a squared times dt by dz equals alpha man. Okay. No, make mistake? No, okay, it's okay, it's fine. So, now only thing is I am going to, for R characteristic will be, R characteristic is A, and T characteristic, because now I am looking at long distances, I am going to choose T characteristic as not u by A by u, but L by u. Okay. T characteristic is L by u, R characteristic A, and theta is again T, the same thing. Theta is T minus T1 divided by T naught minus T1. I am not going to do the theta part again, I am just going to change T to theta, because T naught minus T1 cancels everywhere, right, you saw that earlier. So, now by choosing L by U, I get an L here. When I make Z dimensionless, I will get an L. T will give me L by U. I already have a U. I can take U by L common. Okay, that is one of the things which I want to tell you. Other thing is, when I make it dimensionless here, I will get A squared. When I make it dimensionless here, I will get L squared in the denominator, because I am choosing a different scale. Okay, I am going to make this thing to U by L. D theta by dt star plus 2 times 1 minus r star squared d theta by dz star equals 1 by a squared 1 by r star star plus and I will take the alpha at the bottom. So, let the alpha be here as alpha. Okay. So, remember now this Z star is with L as my characteristic scale, R star is with A as my characteristic scale. So, what do I get here? I divide by alpha again, and I am going to divide by multiply by A squared alpha, all the terms multiply by A squared alpha. A squared divided by alpha. Okay. So, I get A squared U by L by alpha times d theta by dt plus 2 times Z star equals plus A squared by L squared d squared theta by dz star squared. Pardon me? Two, where? No, U has come out here. Are you talking about this? I have taken new factor, I have taken new common. No, you won't have U star because U is average. U is an average velocity, is a constant. This is, we have already calculated the velocity field from the Hagen-Poiseuille equation. So, average velocity is fixed. Okay, yeah. If it is U as a function of R or U as a function of Z, then I am making it characteristic, then I will get a U star, U characteristic multiplied by U star, but this is U itself. Okay. So, this is again Peclet number multiplied by A by L times d theta by dt plus 2 times 1 minus r star squared by dz star equals, now you see the way I have scaled it, because L is much larger than A squared by L squared is much lower. Okay. So, that is what I wanted. I wanted to neglect the axial conduction. So, this is basically going to be very small. So, this is very much less than 1. And so, this can be written as approximate as 1 by r star d by d r star of r star d theta by d r star. Okay. So, I have basically gotten, I have an A by L also here. I have Peclet number multiplied by A by L, but the argument is A by L is small, Peclet number is large. So, Peclet number multiplied by A by L is reasonable, so I am not neglecting it, you understand. You may ask, I have neglected A by L here, I have A by L here, why am I not neglecting that? Because this is multiplying Peclet number is large, okay. So, Peclet number into A by L is of sufficient order for me to retain it here, that is the argument, okay. So, this business of scaling it in a different way is helping me do this analysis of neglecting the axial conduction, okay, relative to the radial conduction. So, now I spoke earlier about doing the analysis. So, now this is my equation, okay, Peclet number into A by L times d theta by dt star plus 2 times 1 minus r star squared d theta by dz star equals 1 by r star d by dr. You know, I am going to forget the stars after some time because this is getting painful to write them. Okay, let me just keep this anyway, a squared by L squared times d squared theta by dz squared. Although this is small, I am just writing it down. I want to do the analysis of this problem in a moving reference frame, because I want to sit on the slug and I am moving, okay, and I am moving with an average velocity, okay. So, basically like I said last time, we analyze this in a reference frame which moves at average velocity u, okay. The average velocity in laminar flow is u, the maximum velocity is 2u, okay. So, I am sitting on this thing and moving. So, what I am going to do is I am going to say this z minus ut, z and t are in the stationary reference frame. So, if I am looking at it from far away, okay, as the slug moves, it occupies z position, that is going to be given by ut, okay, at t equal to 0, z is 0, and then the slug has started moving at a constant velocity. So, z will be ut, but since I am sitting on the thing, this is the moving reference frame coordinate, z tilde will always be 0. As far as I am concerned, z tilde in the moving reference frame is 0, okay. That is how this comes. What I want to do is, and now what we spoke about earlier, long ago, Lagrangian reference frame and Eulerian reference frame. Eulerian reference frame, I said we are looking at fixed position. Lagrangian, we are moving along with the particle, okay. So, basically what I am trying to do is I am shifting to a Lagrangian reference frame, okay, and in the Lagrangian reference frame, d theta by dt plus u d theta by dz is your d theta by dt. This is Lagrangian, okay. So, so what I am going to do is I am going to take in dimensionless thing u becomes 1, I will take one of this outside. I am going to write this as, I am going to write that as Peclet times A by L times d theta by dt star plus 1 minus 2 r star squared d theta by dz, okay. What have I done? 2 minus 2 r star, one of them I have taken along with this partial derivative and made it total derivative, or substantial derivative. This is my Lagrangian. Okay. And now because I have the moving reference frame, Z does not make any sense, Z is only valid for the stationary reference frame. So, I am going to convert this to Z tilde. Okay. So, this is going to be Z tilde and so, why? Because look at this, d by dz will be the same as d by dz tilde. That is the point. Okay. So, when because z tilde and z are linear, I mean just the same thing. So, two things I have done, I have shifted from the Eulerian reference frame here to a Lagrangian reference frame. So, the partial derivative has become the substantial derivative. Okay. The other thing I have done is said, look, this z does not make any sense, I need to do z tilde, maybe z tilde star, because z tilde is also dimensionless. Okay. Z is dimensional, so if I divide by A everywhere, I will get that. So, anyway, or L everywhere. So, this is the thing which we get. Okay. What I want to do is, I want to this particular quantity, what is this? This tells me what is the change of the actual velocity from the mean value. Okay. And what I will do is now write all these quantities, the temperature as an average value plus a deviation from the average value. So, what I am saying is I am going to write theta as theta bar plus theta prime. Theta is a function of r, z and t. Okay. This is actual theta, this is averaged in the r direction. This is the difference of the actual theta from the average value. Okay. Theta prime is the deviation from the average. Why am I interested in this? Because what I want to do is I want to find out how does the average temperature change. If you remember, I told you what we find is we are talking about the average temperature in the radial direction, how does that spread in the z direction, that is the objective. So, I need to do an averaging. Okay. And how do you do the averaging, how is theta bar defined? This is average 0 to 1 theta, I should do 2 pi r dr divided by 2 pi r dr. Okay. This is anyway a constant. So, what I have done is I have just defined the average temperature. Okay. Because theta is a I am only averaging in the radial direction. Okay. So, how does the average temperature change is what we are interested in doing. So, my job is now to actually average this thing. So, what I want to do is I am going to do the average of this equation, which means basically I have to multiply every term by 2 pi r dr and integrate it from 0 to 1. Okay. That way I will get the average. And yeah, so that is what we will do in the next class. So, we will just multiply everything every term by 2 pi r dr. But before that we will do something, we will just substitute for theta in terms of, but point I want to make here is what do you think is going to be the average of theta prime? What is the average of theta prime? What is the average of theta prime? So, you take the average on both sides. When you take the average of this, you will get theta bar. Theta bar anyway is uniform. So, average will be theta bar. So, what will be the average of theta prime? Theta bar minus theta bar 0. My point is average of theta prime will be 0. Okay. How do I say that? Take the average of this expression, average of this definition of this is average of theta. So, theta bar equals theta bar plus average of theta prime. Okay. So, theta equals theta bar plus theta prime. Take average of this, I get theta bar, taking average theta bar is equal to theta bar plus theta prime bar. 0 equals theta prime bar. Okay. So, I mean, and the same thing for the velocity. If you want to find, this is the deviation from the average velocity was u. So, this is u dash. Okay. So, let me do that and then we will stop. So, u is equal to u bar plus u dash. Okay. U is, we wrote it as 2u times 1 minus r star squared. Okay. And this is u plus u times 1 minus 2 r star squared. 2 comes inside, I have taken out one of the u's outside. Okay. If I want to find the average of this, what should I do? I should multiply it by 2 pi r dr and integrate it. So, u times 1 minus, there is a 2 here, okay. This 2 is coming here. So, I am trying to find the average of this deviation. Okay. So, u dash average is this. So, you can integrate this out, you get 1, you get r star square by 2 minus 2 times r star power 4 by 4 from 0 to 1. Okay. So, this gives you evaluate at 0 you get 0, evaluate at 1 you get half, minus half 0. So, you get 0. So, anyway, the point is, I mean, it's kind of obvious because the average, if you subtract whatever is that the difference is going to be 0. So, we are going to use this in the derivation. So, you have to remember that the average of the perturbation quantities will be 0. Okay. So, when you are doing some average, what I am going to do is use this and then we will move forward.